Okay, this is the second part of the lecture for tonight. We're going to talk about raster analysis. Raster analysis is basically when we take different raster data sets, and we do things with them. This usually uses a cell-by-cell function on one or more inputs, and they can be the same size. They have to be the same size so that they line up spatially. A lot of times in the past, it would tell you that these inputs had to be exactly the same, and you'd have to line them up and all this kind of stuff. But now, it'll take care of a lot of this stuff on its own. But basically, it's very much just like what you're looking at here. You have different layers of inputs, and then you'll do things that will multiply values or add values or do something else to the values to generate new and important information. So, first thing we need to talk about is resampling. Okay, if everything has to be the same size and has to fit and has to align, well, sometimes that just doesn't work. You got a 3-meter grid, you got a 10-meter grid, 3, 6, 9, 12, doesn't line up on 10 anywhere. So you're going to have to make some changes, and the changes aren't going to be super neat and super easy. They're going to look more like that one there on the top where you're going to have some things that don't quite fit. Resampling is where you create a brand new grid that's empty, and then it populates it with numbers that it gets from the old data set. 3 techniques that we commonly use: nearest neighbor, bilinear resampling, and cubic convolution resampling. Nearest neighbor simply gets the value from the old cell that falls closest to the center of the new one. Okay? Center of the new cell, what's underneath in the old data set, that's what it gets. That's what it uses. This preserves as much of the original value as possible. It's also the fastest method. Bilinear is different. Okay? Bilinear looks at the 4 it calculates a new value from the 4 cells that fall closest to the center of the new cell, and then it uses a distance weighted algorithm to calculate that out. So what this does is you get this new cell. From the center of that new cell, it goes outward until it finds the center of the 4 closest old cells, and then it averages them together using a distance weighted algorithm. What that means is the ones that are closer are weighed more heavily, the ones that are further apart, further away, are weighed less. And that's bilinear. Cubic convolution is basically the exact same process, except it looks at the 16 closest cells. So it looks at a larger area. It's also the most time consuming. GIS automatically resamples rasters for analysis if it's needed, and it doesn't warn you about this. Resampling can degrade raster quality, and so you should be aware this is happening. So what are the best practices to prevent it? Make sure that all your data sets that you're adding up are the same size, and that they're aligned, and that they're in the common extent, common cell size, same projection, all that kind of stuff. If you do that, then there's nothing for it to automatically do. Okay? And so then you don't have to wonder, did it do cubic convolution? Did it do nearest neighbor? You'll know that it didn't have to do anything. So let's look at some raster analysis techniques. The main ones we're going to look at start with are map algebra and Boolean overlay. So what is map algebra? Map algebra is nothing more imaginative than simply doing math between different raster data layers. And so in this setup, we have 2 input layers. Input grid 1, input grid 1 and input grid 2. Map algebra simply does a math function between these 2 input layers. Now, for purposes of visualizing it, we're looking at 4 cells. This literally could be a raster data set shaped like the state of Virginia. Okay? And in input grid 2 could be a different raster data set shaped like the state of Virginia. As long as they line up, and if you wanted to add, the 2 layers together for some reason, that's what map algebra does. For example, top left corner is a 5, second layer down, top left corner is a 3. If you add 5 plus 3, you get in the output grid an 8, top left corner. That's all it does. Nothing more complicated than that. Map algebra is also useful in conversions. For example, what if you've got this wonderful raster that shows precipitation in centimeters, but you want it in inches? Well, map algebra, input layer 1, multiplied by, well, actually in this case, divided by a function of 2.54, gives you a new output, which is simply the old data set divided by 2.54, and that is the conversion from centimeters to inches. You can also use map algebra to do cut and fill. Cut and fill is it's a tool that was developed for a lot of different things. Some environmental groups use it a lot of times to monitor changes in the landscape relative to construction or mining activities. Companies that move earth for a living, excavation companies, that sort of stuff, they can use it to get an idea of how much material they have to remove and how much space they have to put it in. Now, the interesting thing there is that when you dig out a certain volume of earth, you break it apart, and it then takes typically a larger area to put it back into, especially if it's rock and you break it up. It never goes back together the same, and so you need a larger space. If it's just earth, turns out you can actually usually compact earth back into a lesser volume than it started with, but it won't really be good for anything because it'll be packed too tightly together to grow or support anything. But that's what map algebra does. You take the first layer and then you put in the second layer that you want or whatever, and it'll show you the areas that increased or decreased in size. You can also use map algebra to model equations, complex expressions with multiple inputs to calculate things like a risk or a hazard index. For example, here is one that's looking at the likelihood of erosion, and so it looks at runoff in centimeters based on a couple of different inputs. So precipitation, slope, soil infiltration, and vegetative cover. And so it's got these various different data inputs, and based on that it uses a mathematical equation that you simply input to your layers, and it gives you this new output here that basically shows you the amount of runoff you can expect. You can also use map algebra to do Boolean operations, things that are true, false, like ones and zeros. Very basic things like elevation is greater than 1200, and it goes into your digital elevation model, and everything that's greater than that gets selected or not selected depending on how you set it up. You can also look at things like slope and select certain ranges, and it'll highlight those. Or maybe you've got a field in your not in your attributes. Sorry about that. Maybe you have a data set of some obscure thing like crown cover, where every pixel is graded on some percentage of crown cover. And so you want all the ones that are over a certain range, okay, and all the ones that are under a certain range, or whatever it is you look for. When you put these true-false arguments in map algebra, it simply selects the ones and maps them out accordingly. Boolean rasters represent true-false statements. Slope greater than 10 degrees, you have a slope map on the left. On the right, all the areas that are greater than 10 degrees become green or a value of 1. All the others become a 0 or a pink color. Lots of different Boolean operators, and divided by, raised to the power 2, different things. These are the stuff that we use for things like intersect and union, A and or B, or A and not B. There's tons of these, and the tutorials in the chapter will take you through and walk you through a lot of these exercises. Again, Boolean operators, yes, no, 1, 0, true, false kind of questions, using these different ones like intersect or union, and you can see what you then end up with or don't end up with. More of the same. Alright, so where does the rubber meet the road? What do we actually do with this? Well, let's look at this lodgepole pine habitat model. This is a Boolean habitat model. This isn't a really complicated one. not an index model. It's simply a where meets these two basic criteria. Precipitation over 60 centimeters, elevation above 1,500 meters. If you do that over this area on the left, you'll see this patch that's in blue with a mark of 1. That gets the required rainfall. The map in the middle shows you the elevation values. Everything that is above 1,500 meters is green. Everything that's below it is white. Ones, zeros. And then lastly, you get over to your lodgepole habitat, and basically it's only places that meet both criteria. And so it has to be in the blue and it has to be in the green. And the only space common to the blue and the green is what you see identified there in the end in the orange. And is basically the same kind of thing as multiplication in terms of Borleen data anyway. Ones and zeros multiplied out equals the same thing. You can also create additive models, and additive models are kind of interesting. So you still have ones and zeros, but instead of multiplying them together, we add them together. And so what it does is it gives you a different kind of output. You now have different numbers. Instead of just ones and zeros, you have ones, zeros, and twos. So what do they mean? Well, that's where it gets tricky. A value of 1 simply means it either gets enough rain or it has the right elevation, but it doesn't tell you which one. A value of 2 means it meets both your criteria, and a value of 0 means it meets none of your criteria. Now you could be creative here. Instead of a 1 and a 0, make one of them a 10 and a 0. And if you did that, a value at 10 would mean it met one criteria. A value of 11 would mean it met both criteria. And a value of 1 would mean it met the other criteria. And a value of 0 would mean it means no criteria, met no criteria. So you can be creative with this as well. What are some of the drawbacks? You have simple sort of true-false questions. It doesn't support the gradation of suitability. It assumes everything is equal. The thing we're going to talk about next is a weighted overlay. Weighted overlays is the primary means of creating an index model or a suitability index, which is basically what we're going to do for our class project. And essentially what we do in a scenario like this is we reclassify our input rasters. Well, this is one way of doing it. We reclassify input rasters into rank suitabilities. We weigh each input according to its importance, and then we calculate an index. So we have the weight times the rank equals our index value. And so here is how they did it. This is just one technique for it. They looked at a couple of different things here, and they're trying to look at landfill suitability. So this is where a landfill should be. So their criteria was they didn't want it to have a lot of slope. They didn't want it to have a lot of infiltration. They wanted it to be relatively close to a road. They wanted it to be relatively far away from a stream. And so they classified out their data so that slope would be 0 to 10, 10 to 20, and greater than 20. If it was less than 10% slope, then that means it's relatively flat. That means that's good, so that gets a 3. 10 to 20 gets a 2. If it's more than 20, it gets a 1. All right, makes sense. Infiltration classes. Well, when we look at the infiltration classes, infiltration means how fast water moves down through the soil. Now, in a landfill, you don't want the water to move down through the soil because that's going to leach out the things that you're burying. You want low infiltration. So the places that have the parts that have low infiltration ratings get a value of 3. The ones that are medium get a value of 2, and the ones that are high get a value of 1. Distance to roads. The further away you are from the road, the longer the road you have to maintain, and support. It's just a cost factor. So if it's within 500 meters of a road, it's a 3. 500 to 1,000 is a 2. Over 1,000 gets a value of 1. Distance to streams. Again, you don't want the landfill close to the stream. You don't want runoff and groundwater infiltrating the stream coming from the buried materials. So 0 to 100 meters gets a 1. 100 to 200 gets a 2. And over 200 gets a 3. All right, so the way this would have worked is you would have taken your slope layer, for example, and you would have classified it into these 3 categories. You would take your infiltration and classified it into those categories, which actually would have already probably been in that. You can look at the distance to road, and you would have classified it in those. In the same way, distance to streams. All of this is things that you would do to basically create a ranked classification. And then the next part comes the weight. Now, if you add up those weights, 0.1 and 0.4 is 0.5, 0.5 and 0.2 is 0.7, 0.7 and 0.3 is 1. The way they did it was they divided it all up between 1. You could do the same thing with 10. I personally like to do it with 100 because it gets me away from decimals, which creates some problems sometimes for attribute tables. So, if this were me, it would be, instead of 0.1, 0.4, 0.2, and 0.3, it would be 10, 40, 20, and 30, and they would all add up to 100. Alright, so how does the landfill suitability index work? We take the slope and we multiply it by the weight. We take the infiltration, we multiply it by the weight. We take the distance to the roads, we multiply it by the weight. Distance to the streams, we multiply by the weight. We add those together and you end up with a number. Alright? If you had a 3 in each of the categories and you multiplied them by the weights and added them up, you would end up with a 3. And so your suitability indices runs between a 1 and a 3. And that's how this sort of model would work, and you would get a map that looks very much like what you see on the right. Now we can also use various Boolean conditions. So you might have a combination of weighted ranks and true-false inputs, things like set-off areas and limits, places that you want to make sure that you have a 0 value so you don't consider. You can actually do a lot of creative things in your model process to eliminate things that you don't want to deal with, or places that you can't or don't want to build. So when we do a weighted Boolean overlay, for example, looking for a place to put a cabin, and we're going to look at slope, aspect, and land cover, and we're going to use ranked weighted layers just like we did before. The thing here is Forest Service land has to be off limits. Why? Well, it doesn't belong to anyone. You can't buy it. It belongs to the Forest Service. So you have to take it out of the picture to start with. So you could do a Boolean 1 no layer that would eliminate all those gray areas, and then the rest of the space you could then calculate your weighted Boolean overlay and end up with your index values that you see there on the bottom right, where the high values are a 4, and so the places that are the green color are the best locations. There's lots of ways to do map algebra, but the main one is simply the raster calculator. The raster calculator used to be a toolbar, and then it became part of this tool set. And it literally looks just like a calculator. You simply pick the layer that you want to do something to. Select the layer where it's going to, what your output's going to be, what's going to go into it, and then where it's going to save it and stuff. So, in this example here, if you're trying to calculate out some kind of a thing that's 3.218 times the elevation, you would simply select elevation and then go over to your calculator part and go multiply by 3.281, and then it's going to give you this output. It's going to be in the spot, the one below. You would figure out which folder where you want it and all that kind of stuff. Click OK. It's then going to make a brand new raster that's going to be your elevation times that. So what are some other functions that are available as far as raster analysis? There's lots of them. Reclassification is really useful. That's where you simply go in and you can just change the classes, combine classes, and do a lot of things with that. Surface functions, distance functions, density functions, interpolations, neighborhoods, and zonal functions, they all have their unique spot. And so we'll go through a few of these. So reclassify. Here's a good example. You got slope and it's classified in percent, but for your purposes, you just need to know if it's a high slope or a low slope because you're only going to make two classes. One's going to be good, one's going to be not good. And so you look at the old ones, you go in and maybe you tell it to make 3 classes or 2 classes or what have you. In this case here, they're making 2 classes, high and low. And so the old way that it reclassified the actual slope numbers, it was 0 to 10 and 10 to 90. And then you simply put in what you now want it to be, and so 0 to 10 becomes a 1, and 10 to 90 becomes a 0, and no data stays no data. You have a lot of means to do this. You can change the classification methods Jinx natural breaks, defined intervals, equal intervals, quantiles, you name it. You can tell it the number of classes, etc. You can put them in manually even. There's all kinds of flexibility there. We can also do surface analysis. Surface analysis is typically start off with a DEM, and this is where we measure things like slope and aspect, hill shade, and contouring. And so what are we actually talking about? The top left is a digital elevation model, and so that's just representing the elevation for every pixel. Then from that we can calculate slope, which is the change in rise over run in the steepest direction for each pixel. Then we can calculate aspect, which is the direction of the steepest slope. And then we can do hill shade, which puts the sun in a position in a certain spot in the sky and casts appropriate shadows relative to the DEM. Or we can do contouring, where we create lines that go across our surface at fixed levels of elevation. So you start off at a spot that's at 1,000 meters in elevation, and it literally just tracks where 1,000 meters is. And so as you move from one pixel to the next, it just keeps going and trying to stay as close to that 1,000 as possible, so that you get these lines, knowing that what these lines are in effect are level across the surface. So let's look a little bit at slope. You calculate slope on the surface based on the surrounding cells. It can be expressed in degrees or percent. Slope is basically just rise over run, but if you take the tangent of slope, you get degrees. Or percent is just rise over run times 100. Aspect calculates the direction of the steepest slope. And so you're standing at a location, you figure out your steepest slope, and that is the direction of your aspect. And it's basically which way the hill is facing is the easiest way to think about it. It goes from 0 to 360 degrees. The thing to remember is 360 and 0 are both north. Hill shade sets the sun at a certain spot and the angle at a certain one, and then it reflects what the shadows might look like based on that. View sheds are something else we do. View sheds are, like a watershed identifies all the areas that drain together. A view shed simply identifies everything you can see. So you create a point as an observer, you set the height of the observer, which is basically how high your eyes are off the ground, and then from that it simply does a what can I see from here calculation. And in this example here you can see the spots that you can and cannot see. Cut and fill, we've talked about that before and what that is. I'm not going to really spend too much time going back over it. You take your initial surface and your final surface, and it tells you the difference. The places that are in cut means it's things that you removed. Fill is the places that you added in. There's also a lot of hydrologic functions that are out there that we can use and do in GIS. We can derive streams and watersheds and all kinds of other features, all based off of a single digital elevation model. We can also calculate distance functions. Distance functions are really awesome. For example, we might have a cost path distance where we have a cost surface that could be something as simple as slope, and so we're trying to minimize the amount of steep slope we have to go through to get from point A to point B. And a cost path distance is how far that is, keeping in mind that we want to maintain a certain level of slope. We can also do basically a buffer where we go a certain distance from a feature. Bottom left, you have the areas in blue that are a set distance away from the roads being the black lines. Or we can create a distance raster surface. A distance surface is what you see on the right. In a layer like this, every pixel on the entire grid, if you go to that pixel and look at the value that's there, that value is the distance from that point to the closest line or road or whatever these things are there on the right in black. And so that's how that kind of works. Euclidean distance starts from a set point. It creates a grid where each cell represents the distance to the closest feature, and it gives it to you in the same units as the coordinate system. And that's what Euclidean distance is. Euclidean direction is often created with a distance function and indicates direction of travel to the closest road. So you're standing here, and not only does Euclidean distance will tell you how far it is to the road, this would then say, okay, which direction is that. So it's not just the how far from here, it's if I'm here, which direction do I need to go to get to a road the closest. Buffers, yeah, I'm not going to talk anymore about that. I think we've covered that pretty good. It's just an area defined by distance from an object. Alright, so let's look at some things here. Reclassifying stuff, how can we do it? We start with the same raster, ones and zeros, 0 to 300, 300 to 900, which is correct or which is incorrect. It really matters on what you're going to do, okay? For mapping purposes, maybe the one on the right looks better if you want people to know what those numbers are. For modeling purposes, you can't add in a 0 to 3, okay? It needs to be a number, and so 1 and 0 tends to work better. Lowest cost path, basically you create start and stop shapefiles, you create some sort of cost grid, you calculate a distance. It's not just like falling out of a wagon simple, but it's very manageable, and it will eventually identify that lowest cost path. I want to talk briefly about interpolation. Interpolation is prediction of values in between measured points. So you remember the story of Johnny and how Johnny was at home, his dad was at work, his dad come home and asked his older brother Eric, he said, "Where's your brother Johnny?" And Eric said, "Johnny's outside." And Paul said, that's Dad said, "Where's Johnny?" And he said, "Dad, Johnny's outside." And Paul said, "Where's Johnny?" And he said, "Johnny's outside." He said, "Damn it, Eric, outside's an awful big place." Well, that's the same way it is with with data. To have measured points everywhere, it's just impossible because everywhere is an awful big place. So we measure periodically or sporadically or randomly or along a transect or a grid, but we don't measure everything. But we want a complete total surface. So how do we do that? Well, in this example, you've got all these data points, and maybe it's elevation or maybe it's something else. Whatever it is, once you have these points, you can use a technique called interpolation, and it basically creates an estimate of what whatever that number is would be for everywhere else. And so it guesses or estimates or predicts the in-betweens. And there's lots of techniques, and we'll look at a few of them. So here we have sample points from climate stations looking at annual precipitation. So each of these spots is a rain gauge, and they're measuring how much precipitation occurs per year. We want to know how much rain falls everywhere, so we're going to interpolate those values from those known points. Thing to remember here, interpolation is not truth, okay? It is not. And here I'll give you an example to explain why. On the left, we have actual elevation data, all right? And so you can see how the white and the pink and the browns and the yellows and all that sort of space around. Now we use the exact same color to elevation scheme on the right, but just from the peaks, which are the bulleted points over there on the left, we created an interpolated surface of what that would look like, and you get the thing you see on the right. And you noticed how the whites and the purples and the browns and the oranges and the greens don't look the same. That's because interpolation is our best guess between surfaces. It is not the actual surface. It's not the truth. So as far as methods, there's a couple four that we use pretty commonly. IDW, splines, Kriging, and trend. Density functions are something else we do. Density functions look at the rate of occurrences of things. It appears very similar to interpolation, but they are calculated very differently. Interpolation predicts values between points using one of those mathematical methods we just talked about, whereas density functions count occurrences within a given radius and then divide it by the area. So what does that mean? All right, so maybe we look at a 1 mile circle. How many points occurred in a mile? 7. So then that gives us a value of 7. And we go to the next cell over. We look at, again, a 1 mile radius. How many occurred there? 7. Move the next one over. How many occurred there? 6. And so that becomes a 6. And ultimately what that does is, if you look at this map, you see how it goes from the darker colors to the lighter colors. That is when the number of occurrences of whatever it's mapping decline. where more measurements take place, it becomes darker. And so it's an indication of the frequency or the density of whatever the occurrence is, not the value of the occurrence. So we do density functions in two ways, simple and kernel. Simple sums the attributes up, like population, for example, for points within a certain radius, and a larger radius makes your data smoother. Kernel density first spreads values at points out to the search radius, and then it uses some sort of a formula, and then the density is calculated again. When you use the trend or the kernel function, it tends to give a smoother result for a particular radius. It's just a different way of doing the math. So what does simple density look like? Like this. Here you can see looking at line density at 50 kilometers versus 100 kilometers. I want to talk about neighborhood statistics. Neighborhood statistics are kind of interesting. Basically, it calculates a statistic for a specific window, and there's different types of windows. You can use a rectangle, a circle, an annulus, or a wedge. And that defines the area around each cell that is calculated. And then you pick the statistic you want: majority, minimum, maximum, mean, minority, range, sum, standard deviation, whatever it is. It will calculate that statistic for within the area of that box that you specified, or your window. Your window can move in one of two ways. It can move in a block function where, for example, if you use a square, once the cells in square A are done, the next cell, the next block, block B, doesn't overlap with block A. It just moves right along to the next one. Whereas if we use neighborhoods, we define that same window, and we're calculating for that center cell, and that center cell simply moves one row to the right, and that window moves one row to the right with it. And so there's significant overlap. Obviously, block functions are much faster than focal functions. And here's what they would kind of look like. We take some land cover data that's kind of rough. We use a 4x4 focal majority function. What this will do is it looks at a 4x4 cell and it says, okay, what's the major value here? And so if we're looking at something like land cover, we're going to have different classes: class 1, class 2, class 3, etc. When we use a 4x4 function, imagine a 4x4 grid. So that's 4 cells across, 4 cells down, and 16 cells. It looks at those 16 cells and says, what is the single biggest value we have here? Is it class 1, class 2, class 3? If it's class 3, it becomes class 3. If there are cells that aren't class 3, they become class 3. Now, if we do the same thing instead of a focal function, if we do it as a block function, see how much more grainy it looks than what it does over here? One smooths it out, one really blocks it up. And so this is just showing you how neighbor function works. You can go back if you want to spend the time to look at this. Your target cell is the one in the middle. There's your window. If we're averaging it, if you take, well, let's just add them all up for the heck of it. 4 and 4 is 8, and 1 is 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 4 makes 23. Divided by 9. Comes out to about 2.5, I guess. That is all it does. It takes all those cells in the middle, averages them. That's the new output. As that focal window moves one box to the left, the first column on the left gets replaced with the next column on the right, and you do the next calculation for the next cell over. Neighborhood focal mean smooths rasters. The effect grows larger as you make the size bigger. This is really good for getting rid of noise. What is noise? Noise is that sketchy kind of edgy stuff that happens where, for example, you've got a boundary between two things and it's highly irregular, and so your line jumps all around back and forth, and your raster is sufficiently sized so that you pick up a bunch of that, but you're kind of trying to look for like a smooth line, and instead you're getting a really rough, jagged line. Using a focal mean will go through and it'll calm that down a lot, and so you can see how you have all this fine detail on the image on the left, but when you get to the image on the right, it is much, much smoother, almost like you sort of tried to wipe it away. and that's effectively what happens. And here's an idea or example of this. So we've got this slope map, and we're trying to classify whether something is high slope or low slope. So we pick an arbitrary value. Maybe it's 9%. Everything below 9 becomes 1. Everything above it becomes something else. All right? But yet, we're trying to map out large, like polygon-sized areas of this stuff, not individual cells. And so when we look at that image there on the top left, and you see a lot of those really fine detailed things, that just creates problems for some analysis. It's not what we really want. We're more interested in those areas that are mostly purple, not the places that are mostly fuchsia or turquoise or whatever that color is. So if we use a 5x5 majority filter and we run it through a couple of times, it goes from being the one on the top to being the one on the bottom, which is a much more realistic looking kind of feature, particularly if our long-term goal is to convert that raster into polygons. So if we go from raster to vector, creating vector, that top one's going to give you a whole lot of polygons that have almost no meaning, where on the bottom, much better to work with. And so the way that works, it shows you over here on the right, is that you have these boxes, and basically in an individual box, the most frequent value in the neighborhood becomes the center value of a new cell. So you draw a box, and whatever is the most inside of it, that's what becomes in it. Zonal functions are similar, but they're quite different, really. It still has this concept of a window, and it still does the same kind of calculations, and it still moves the same kind of ways. The difference is, with a zone, it's not a set sort of shape like a 4x4 or 5x5 window. You specify the zones, and the zones literally could be another data set, like census blocks or tracts or counties or whatever it is. You could say, okay, using this as zones, calculate these statistics. And so it would let the zones define the area that it's looking at. Take the data that you told it to take from the other data set, and then calculate the statistics you request on that, and then populate a new data set with those numbers. So what is a zone? Areas that have a raster or feature data set that share the same integer values. Yeah, that's one way of looking at it. Zonal statistics. The zones are defined by the zone layer. In this example, we're using watersheds. And when the statistics we want is the average slope. Why would you want to know the average slope in a watershed? Okay? When you get a heavy rainfall, the amount of discharge from a watershed is directly related to a lot of things. But the steepness of slope will reflect how quickly the water exits the watershed. Okay? So a watershed with a steeper slope will discharge its runoff much faster than one that's relatively flat. And so this gives you a way of determining how prone something might be, for example, to a flash flood. So we have all these watersheds, and we have a slope map. We can simply average up the slope within the watershed. The one that has the highest average slope, most susceptible to flash floods. Okay, so zonal statistics aligns, same kind of scenario, different things you can calculate. Again, working through the tutorials in the chapter, you'll be amazed at some of the things that they'll show you how to do. Same way with points.